So we continue with this example determining our probabilities. Now keep in mind that as we calculate probabilities, they're written as A over B. I'm going to put it right up here, A over B. A is the event in question, and B is the size of the sample space, or how many ways something can occur. And A is always a subset of B. So this example says the combination for a lock on a briefcase contains 3 digits. What is the probability someone can unlock the clasp by guessing the number if, and then we have these 3 questions here, A, B, and C, if the numbers can all be the same. That's for A. So if the numbers can all be the same, I'm just going to put the numbers here. Here's the first one, here's the second one, and then here's the third one. So there are 10 possible digits, 0 through 9. So this number can be any one from 0 through 9. So there's 10 possible digits for the first number here. Since this can be the same as this one, there's 10 possible digits for the second number, and the same for the third number. Now logically, if we were to go ahead and make the sample space, maybe the sample space would look like this. We would start off with 0, 0, 0 would be the first number, 0, 0, 1 would be the second number, 0, 0, 2. And if we were to continue with this pattern for the sample space here, we would probably end up with 999. So logically, just looking here, the sample space would go from 0, 0, 0 all the way up to 999. That's 1,000 different numbers that can be assigned. Using the fundamental counting principle, if there's so many ways to assign the digit to this number, so many ways to assign the digit for this one, and so many ways to assign the digit for this one, how many altogether? Of course, we simply just multiply, and of course, this is 10 to the third. 10 to the third, there's 1,000 possible numbers that can be assigned. That's the sample space, that's our B. The event, A, that's the one number, that's the correct number. That'll get you to open the clasp. So that's 1 out of 1,000. So this can be written as 0.001. That's 1 out of 1,000. And of course, we recognize this as 0.1%. So it's very small. We're going to do the same approach, use the same approach for letter B. Except B says the numbers must all be different. So if there are 10 digits that I could assign to the first number here, this number must be different than this one, so that leaves me with only 9 digits. And of course, this one must be different than the other 2, so I'm left with 8 digits. Using the fundamental counting principle, we just go ahead and we multiply. This is the same as 10 permutate 3. And 10 permutate 3, well, 10 times 9, that's 90. 90 times 8, that's 720. So there are 720 different ways to assign the numbers if the numbers must all be different. That's our B. Of course, there's only one correct number. That's 1 out of 720. So we can use our calculator. 1 divided by 720. So that's approximately 0.0014, and of course we recognize that as 0.14%. Not much better than letter A. Then finally for C, there is a lock for each of the 2 clasps on the briefcase. So this briefcase has 2 clasps on it. Each clasp can have its own lock number, in which the numbers can all be the same on each lock. So rather than having 3 numbers, I'm now going to have 3 more. So there'll be 6. And each number can be the same. So I've got 10 here, 10 here, 10 here, 10, 10, and 10. And of course, according to the fundamental counting principle, how many altogether? So this is 10 to the 6th power. 10 to the 6th power, that's 1 million different numbers that can be assigned. That's our B. There's only one correct one. So that's 1 out of 1,000,000. That's 0.00001. And of course, we know that as 0.0001%, very small, I'm guessing the combination for these briefcase locks. And there you go.